needs no introduction.
Exactly. Yeah.
I was looking forward to the talk because the title on the webpage is Real Processing in Memory. So I was sort of looking forward to seeing what real is, but the title seems to have changed. So
so I changed the title. I don't know who put the title in the website, actually. But actually, I'm going to talk about algorithms and architectures for digital processing in memory. So the talk will be about processing in memory. And I have some nice slides about motivation for processing in memory. Some of them are actually based on data from Subhashish and Monur. So I'm skipping those slides, and I won't talk about why we need to process in the memory, or what are the limitations of processing in memory, as Mark talked about. I will just start by talking about a specific type of processing in memory, something that we call Memoristic Memory Processing Unit, or mMPU. It's one type of a special real processing in memory architecture. But most of the talk will be about algorithms for processing in memory. Again, it will be more tailored to the mMPU, but it actually can be generalized to other types of processing in memory architectures and different system and architecture aspects of that. So since I'm a bottom-up guy, I will talk in the first part about the low stuff, like about the circuits and how it works. I know that most of the audience, this is not what you are looking for. So if it's too low level for you, read your emails, and in a few slides it will end. But most of the talk will be about more the system and the architecture and algorithms aspects of that. So we will talk first on how we build the mMPU specifically, and then, assuming that you understood something and you understand how it works, it will become like a black box that is doing what we want it to do. And we'll talk about how we perform arithmetic operations within the memory, and then how we improve the reliability of processing in memory, and then some aspects of programming and architecture and microarchitecture of processing in memory. And at the end, I will briefly talk about two applications, one attractive application and one application that, at least for this type of processing memory, we think that is not a good application, and we will conclude. So mMPU, the first M is for memory stores. I think that this type of slides were mentioned in a few talks earlier. The idea is to use resistive memory with different names: resistive RAM, phase change memory, MRAM. Doesn't really matter. We can work with all of them. And I do want to explain how it works, at least how we are doing that. So all you need to do to understand from the device level, there will be no band diagrams or something, just some illustrative way that this device works. It's basically a resistor. So you put voltage, there is current, and the ratio is the resistance, Ohm's law. But unlike regular resistors, in a memory store, the resistance can be changed. So if we apply voltage or current in one direction, then the resistance will drop, which means that you can see here that we have a voltage and the current is increasing because the resistance is lower. And since it's a physical device, there are some limitations. So there is a low resistive state, the lowest possible resistance of the device. And if we put voltage or current to the other direction, then the resistance will increase. And you can see this, that although the voltage here in its magnitude is higher, the current is not increasing anymore. And again, there is some maximum value, which is called high resistive state, or ROF. And if we don't apply any voltage across the device, the resistance is constant. So it's a non-volatile device. No voltage means that the value in the terms of resistance is unchanged. And using those kind of devices, we can build memories. So we store the information in the form of resistance. We put it in an array. We have rows and columns, or word lines and bit lines, and every cross point is a memory cell that stores data in the form of resistance. And since it's a memory, we need to read and write from it. So if we want to write, we just need to apply the voltage, positive or negative, according to the values that we want to store. So we will select a device. We'll put a ground in the word line. we'll put in the bit line positive or negative voltage, and we'll get 0 or 1 or high or low resistance as we want. And if we want to read, then we will use Ohm's law, which means that we will put low read voltage, low voltage, so it won't change the device, so the change will be negligible, and we'll sense the current, and the ratio is the values that we want to sense. So that's a memory, but we are talking about processing in the memory. So
if you apply it repeatedly, it's changing the value?
So it really depends on the technology. As I mentioned, there are many technologies. In some, they're so nonlinear that low voltages won't change. Or besides, I will talk about reliability. Sometimes it is, but it's not a desired phenomena. Some will change, and it means that we need to refresh them or to sense it. But different technologies have different behavior on that. So this is how it works as a memory. But we want to compute. So the idea is to take the same structure of the crossbar and to give it also computing capabilities. And there are many ways to do that. I will talk about something that is called stateful logic, which means that we use the same way that we store the data, resistance, also for compute. So we compute on resistors, using resistance as the logical value, unlike, for example, CMOS or most ways that we compute where we use mostly voltages. And I will show an example of something that we called magic, memory-store-added logic, but it's just one example out of many. So this is an example of a magic NOR gate. A magic NOR gate consists of 3 devices. 2 are the inputs. So the initial resistance of the value of the devices is the input. If they are in high resistance, we call it 0. If they are in low resistance, we call it 1. And the third device is the output. So it's final resistance at the end of the operation. That's the result of the calculations that we did. And the way that we compute is in 2 steps. In the first step, we'll initialize the output to the low resistive state, which is equivalent to 1. And then we'll apply voltage, positive voltage here, and we'll put ground here. So now current will flow from the positive voltage to the ground. And the value of the output depends on the values that were stored in the input. It's a voltage divider. The ratios of the resistors will determine what is the voltage across the output. So if both inputs were in 0 in the beginning or high resistive state, it means that most of the voltage will be here because the voltage goes to the high resistors. So most of the voltage will be here. Let's assume that the voltage here is almost 0, negligible. So it means that it won't change anything. So it will stay in logical 1. In any other case, at least one of the resistors here will be in the low resistive state. 2 resistors in parallel, they go with the low resistance. So in total here, we will have low resistance. And now the voltage will be divided between the two parts, between the inputs and the output. So now we'll have a voltage here that will be sufficiently high to change the resistance of the output, which means that it will switch to 0. So that's exactly the truth table of a NOR gate.
Do you know how much charge is required to flip a memristor compared to like a CMOS gate? Is it much more?
It's much more energy that's required, yes. That's true. It's much more than if you compare a CMOS gate to a stateful logic gate, in terms of energy, the energy for a CMOS gate is much lower. But since we will do it in the memory, we eliminate the need to move the data, which, as Mark and Dave Peterson talked, that's most of the energy and not the switching of a gate.
Because you had to drive a line to get it to memory anyway.
Exactly. That's where we get the benefits, not from the single gate. If you compare one gate to the other gate, definitely CMOS wins. There was a...
If you have, let's say, a 0 and a 1 here, how do you make sure that the memristor on the value of the memristor on the left doesn't change when you're executing this?
So it really depends on the technology. There are some conditions. Actually, we had a paper that showed that for some technologies, there is input instability. We showed it experimentally for specific technologies. And then we offered other gates that compensate on that. But it really depends on the specific conditions of the switching between on and off. And that's because if you think about it, they are connected in the opposite polarity. So what happens to them is different. But that's completely true. It's actually, for many of the technologies, this type of gate has input instability. I actually even have, I think, in 2 slides, just the experimental results for that specific work. The next slide.
Why do you call it magic?
Why do I call it magic? It's memristor-added logic, and also because it's a nice name. I once gave a talk, and someone told me that every time I say, we are doing magic, and it sounds, but it's a nice name. People remember that.
But I'm waiting for the magic, right?
Yeah. But it's not magic, because we can prove it, we showed it experimentally, and that's exactly the paper that I've mentioned, that we showed. Here we show OR gates and not NOR gates, because we show in the beginning of the paper that for this specific technology, NOR gates have input instability, but we showed OR and other gates as well that can be complete logic structures, so we can compensate on that. For this specific, it's called valence change memory. It's a specific type of memory, but other gates can work as well. So this is an experimental work that we did with Rainer Wasser from Aachen and Jülich in Germany. And we also did experimental work, for example, with phase change memory that also was mentioned several times this week. And this is a joint work with Eric Popp from Stanford that we showed that we can build similar gates with phase change memory. So on the gate level, it's working. But we want to do it not just like to take 3 devices and to show that we can compute, but we want to do it inside the memory array. So the idea is to take this structure and compute inside that. And actually, if you look, for example, on the NOR gates that I showed earlier, and now it's marked with colors, so it will be easy to follow the connections, an equivalent circuit is this circuit. You see, if you will follow, you see that all memristors are connected through the red line, and here all the memristors are connected through the red lines, and it goes the same with the other colors. So actually, this is a row inside the crossbar. So we can just apply voltages across the bit lines and get, in this case, NOR gate within the crossbar. And not only that, but we actually can have more than one gate because we apply the voltages only across the columns. So actually, we have multiple gates that can work independently across the different rows. So this is actually a SIMD engine. It's a vector machine. We can perform operations on the vector simultaneously.
It looks to me like a PLA plane.
It's not no, but in PLA you basically put the inputs and then you get the outputs in the outside.
You need 2 of these planes.
Yes.
But the PLA is kind of died out because in CMOS you need 2 devices. Here you need 1 device.
Yes.
So it seems that you would be back in business if you ever wanted.
Yeah, but
it's another avenue, I think.
Yeah, so I think there works about PLAs with memristors, for example, but unlike PLAs, here all the data is inside the cells themselves. You don't need to move them outside, which is a different way, which has its own pros and cons. Anyway, so this is a vector machine, amazing vector machine because we can do it on the entire rows of the array. And we can do logic gates, for example, NOR. So with NOR, we can do everything that we want. So this is the low-level stuff, OK? So you saw now an example on how we can do logic gates inside the memory array. From now on, we will talk only about this illustration. So the idea here is that we have an array. We have in blue here, we have the inputs. In green, we have the output. We can select what will be in blue and what will be in green, because every square here is a memory cell that we can be either an input or an output or intermediate result or just a memory cell that is inactive in any time. And it can be magic gates, but it actually can be something else. For example, here what we see is DRAM. And actually, this is something that Onur showed in his talk to perform computation inside DRAM. This is a paper by Onur. So we can take, for example, DRAM and do it with DRAM or do it with a different type of a memory, as long as we are using the memory cells and we select the different memory cells for computation. This is the same abstraction that we are using. Okay, so from now on, we don't really care if it's memristors, stateful logic, not stateful logic, whatever. This is what we want to do for the rest of this talk. And yeah.
Is the address register in the business? Can you dereference?
Yes, I will talk about those kind of things. Yeah. Okay, so what we achieved here, we saw we have a lot of parallelism among rows, and since crossbars are basically symmetric, in some cases, okay, it's not only but symmetric, but it can be symmetric, then we can have the same parallelism among columns with the same principle. So that's one type of parallelism, okay, a SIMD machine among rows or among columns. But we have more parallelism in this machine. Another form of parallelism is that we can have partitions, which means that we will put switches between different cells in the row in the cost of area. Okay, we will lose area because we will put the switches, but we will get more parallelism because we will be able, within the same row, to have multiple gates. And by that, we will have partition parallelism in addition to the row or column parallelism. And not only that, we also have, in the memory, we don't have one array. We have actually thousands or hundreds of thousands of arrays. So we have crossbar parallelism as well. So we have another form of parallelism. We can have multiple arrays that are performing multiple computations, and in each array they have among partitions and among rows. So if we summarize everything that I said about the mMPU, we're using memoristic technology, but we saw that it can be applied also to other technologies. We perform stateful logic within the crossbar, and we have three forms of parallelism: within rows and columns, within partitions, and within crossbars. So we have a memory that can perform millions of operations simultaneously in the form of logic gates. And the last thing that I want to say about the mMPU in the terms of describing it is about neuromorphic computing. That was also mentioned this week. This is not neuromorphic computing. It's very different. Usually when people hear processing in memory with memristors, they immediately think about neuromorphic computing. This is something completely different. First, neuromorphic computing is analog in nature. This is completely digital. Second, neuromorphic computing is mostly for neural networks. So the basic operation is multiply accumulate using Kirchhoff's law. Here, the basic operation is a logic gate. And it's more like for, I would say, general purpose computation. I will mention later on a few applications, but it's not necessarily a matrix vector multiplication. Actually, matrix vector multiplication can be done, but it's much less efficient for that. And that's the application that I will mention at the end that is not something that is too attractive. And also the role of the memory cells of the memristors is very different. In neuromorphic computing, the memristors are used to store the weights and to perform some computation on the weights. Here, the memristors are the input or the output or intermediate results. They are doing different roles throughout the computation. And also, since neuromorphic is analog, we need analog to digital and digital to analog converters. And here, since everything is digital, we don't need to convert, and we also don't need to move the data outside of the array during the computation. So we also don't need to read during the computation. Now, it doesn't mean that mMPU is better than neuromorphic or vice versa. It just means that it's different. Okay? And it's important to understand the differences, but it's not that one is better than the other. Yes?
Is it easy to move data? Like, say you wanted to take a row and shift everything to the right.
I will talk about that. Yeah, I will show algorithms for that. Okay, so with that, let's talk about algorithms. So the first thing that I'm going to talk about is arithmetic, how to perform arithmetic operations using processing in memory. And all the work that I will mention from here on is a result of the work of those people. This is a picture that was taken last week. Orion and Rotem got their PhD. Most of the things that I will show are from Orion's PhD. He worked a lot on algorithms for processing in memory. By the way, he is the youngest ever PhD student at the Technion. He graduated at 21. Broke the record of his brother. And I will tell you that in the commencement they said that he was 22 years old because he graduated and he had birthday later on. And all his family came to me, why he's 21, not 22? And Rotem worked on other aspects of algorithms that I won't talk deeply, but I will mention later on. And we couldn't do it without the contribution of Ronnie Ronen, who is a senior researcher in my group, that worked closely with Oriane and Rotem about their work. And the first work that I want to talk about is the arithmetic thing. It's a paper that is called the RITPIM. And it recently got the best paper of the journal. And what we did was to support fixed point and floating point arithmetic operations, so addition, subtraction, multiplication, and division. And we saw that there are several ways to do that. First, it can be either bit serial or bit parallel, which means bit serial means that we are calculating one bit at a time. So we first start with the least significant bits, and we do the other bit, and until we got the most significant bit, a sequential of operations. And the other approach is to do bit parallel, to compute on multiple bits from the numbers that we want to calculate. And the other dimension of calculations is whether it's element serial or element parallel. We want to do vector operations. So in element serial, we are working on a single element from the vector every time. And in element parallel, we are working on multiple elements or the entire vector when we perform the computation. Of course, element parallel is more attractive than element serial, so I will talk only on element parallel in the examples that I will show. But if we talk about bit serials, then element serial and element parallel are basically the same, but we are not exploiting the row parallelism, for example, that we have. When we talk about bit parallel and element serial, actually, this is something that can be done, because the idea is that we use multiple row parallelism to calculate different bits from the same element. And Rotem worked a lot on that. She developed a tool that is called Simple Magic that exploits the parallelism within the element. And many people are taking this approach, but actually after she finished this work, we concluded that we should focus much more on element parallel, because we can maybe make a single element faster, but we can get most of the performance benefits from working on multiple elements simultaneously from the SIMD engine and not from improving a single element. So I will focus on element parallel for bit serial and bit parallel. And something wrong. Okay, and just the last thing that I want to mention, and I will go to that later on, you can see here that we basically proposed algorithms for all the different combinations, and the numbers here are the improvement compared to a GPU, and I will later on explain how we measured them. So let's talk first about bit serial fixed point addition. So we want to perform addition on fixed point numbers, one bit at a time. So this is pretty straightforward. We have multiple elements, and we want every time to add xi with yi and get the result inside the memory. We are using that in the same row. So because we have row parallelism, we can do that on all rows simultaneously. Let's assume that we want to do ripple carry header, for example. Then what we need to do is to take n-dimensional vector of x and n-dimensional vector of y, add them together, and we also already saw that the size of the vector doesn't matter. The important thing is what happens within the element. So first we will perform a full adder based from, for example, NOR gates on the least significant bits, and then we'll do the full adder based on the carries that we got from the least significant bit on the second bit, and we'll continue until we reach the most significant bit, and then we will have the entire result stored in each row for each element. Okay, pretty straightforward. The important thing here is that it's not that it's independent on the vector size. And when we want to move to floating point, things becomes much more complicated, because in floating point, it's not only performing addition. We have also the exponent and not only the mantissa. So what we need to do is something a bit different. So let's see it through an example. Let's assume that we want to add those two numbers, 9.7 times 10 to the power of 8 plus 6 times 10 to the power 7. And now, first we need to normalize the exponents. So we are aligning the mantissa according to the exponents. Now we can perform the addition of the mantissas. And then we need again to normalize the mantissa so it will be in its format. And if we think about that, then the addition of the mantissas, that's exactly a fixed point addition that we saw earlier. So this is solved. But the normalization is much trickier. And so we need to do two normalization operations, which are basically performing shift of the numbers. But it's much trickier. And the reason that it's trickier because we want element parallelism. And what?
SIMD, it seems tricky because each alignment's different.
Exactly. Each alignment is different. So for example, here, we want to shift by 5 this element, and by 3 this element, and 1 and 2. But the entire idea is that we have the same control signals. If we will have a different shift amount to each row, then we won't be able to have this parallelism. Or that we will have to build a complicated control mechanism that actually reads the value, and we don't want to read the value. And we actually solved that by doing logical operations for the shift amount, for the shift itself. First, we're using maxes. So logical max can be done, for example, with NOR gates. So we can see that a performance shift can be done with a max. And since the shifts are actually logarithmic shifts here, every bit here, every time goes a logarithmic manner. So in the first, if this is the shift amounts of all elements, then here we need to shift by 1. Then we need to shift by 2. Then shift by 4. And this way we will do it. So it's a sequential operation of logical shifts that can be performed by maxes. And every time the max need to decide whether between 0 and 1. So it is selected by the shift amount of the specific bit. And by that, we don't need to change the control mechanism. The control is identical, but the result of the shift is different. So this is how we get the parallelism without changing the control mechanism. And this way, we can have addition with a latency of n log n. What about subtraction? So in subtraction, we need not only to do right shifts, but also left shifts. So the algorithm is a bit more complicated, but it's the same principle, so I won't cover it in this talk. So that's about bit serial element parallel. If we want to move to a bit parallel, which means that we will use partition parallelism as well, because partitions allows us to work on each bit independently within the same row, then we can get even better performance and better results for the different operations. And so the idea is to use the partition structure to get the best throughput and the lowest latency. For example, we can take a 32-bit number and put each bit in a different partition, and by that we can decide what we are doing within each bit simultaneously or not simultaneously, depending on the algorithm. But before that, let's dive a bit to the partitions and understand what they give us. So for example, we can work with partitions in a serial manner, connect all the partitions together, and now we have just one array. So it's a serial operation, just like without partitions. So that's a possibility. We don't have flexibility this way. We have the maximum flexibility because we can select cells from every partition and do the operation for any other partition, but we don't get parallelism in this manner, not partition parallelism. The other side of that is to disconnect all partitions, and now we have maximum parallelism, but we don't have flexibility because the operations can be done only within the partition. So the inputs and outputs must be on the same partition. And we can, of course, have something in between. For example, disconnect half of the partitions and connect all the others. And by that, we have more flexibility and more parallelism, but limited. And we can do something completely different, but then the picture will be more complicated. And in the paper, we show the benefits and how to support the control, how to make control that is more efficient by limiting the ways that we select, because we don't want to have, we can decide that we have all the combinations, but then the control will be more complicated, and at least for those algorithms, we don't need the maximum flexibility. But we want some flexibility. And for example, if we want to perform shift, like the question that was, so for example, if we want to do shift, like moving an element from one partition to the neighboring partition, but to do it for the entire partition, for all partitions, then we can do it, for example, in 2 cycles. How? We will connect only pairs of partitions together. We'll move them to the neighboring cell. And then we'll connect the other pairs and move them to the neighboring cell. So in 2 cycles, we performed shifts. So we got a lot of parallelism, but we had to pay only 2 cycles. So that's one example. Similarly, we developed different operations using partitions. We called it a partition toolbox. So in addition to shift, for example, we can do broadcast, which means that we want to take a value from one partition and broadcast it to all other partitions as well. And this takes logarithmic time. We can reduce, like taking elements from all partitions and do some operations that will put them in one partition at the end. This is also logarithmic time. And we can do prefix, which means that we will rely on all previous partitions for the same for a specific partition, but for all partitions, this is also a logarithmic time. So this is a toolbox for different operations that we can be done inside partitions, and this will be the toolbox that will be used for supporting arithmetic operations. For example, this is how we perform a multiplication. I won't go into the details. All the details are in the paper, but it takes a latency of n log n to perform the multiplication. We can also do division based on a Carey-Lucas. Pierre Emmanuel showed it for addition yesterday. So this is how we do division, and it also takes n log n latency time. So the idea is to use the partitions and the partition toolbox to support arithmetic algorithms. And for the evaluation, what we did was to take vectors of the size of 64 million elements, building on a memory that is equivalent to the memory that was used for the GPUs that we measured. And we implemented the system for the mMPU based on a paper from Micro 2021 from a group from the University of Michigan that they took magic and implemented the system. So we took the same architecture that they built. And we compared the throughput compared to the GPU, and you can see that the improvement is enormous, right? It can be, for the best case where we have a bit parallelism, we can get 150x for division, and it can go to 700 for addition. So the throughput here is amazing. So that's about arithmetic.
Can I ask a quick question?
Yes, sure.
Throughput is meaning, how about energy?
I will talk about energy.
Did you talk about control? How are the instructions coming?
So I will talk about that when we talk about programming and architecture. Okay, so that's one aspect. We can do different operations, okay, with, for example, arithmetic, but you can think about other algorithms as well. What about reliability? One of the main challenges in emerging technologies is reliability. I will focus today on soft errors. Hard errors are actually hard problems that also need to be solved, especially for stateful logic. But for soft errors, there are 2 types of soft errors. One type is indirect errors, which means that we don't access the device, the memory cell, but something happens there. So there is some error. For example, retention issues. So the bit flipped throughout time because of some unexpected phenomena, or disturbance that we access one device, but other devices were influenced without intention. Radiation problems, all sorts of things. And usually the solution is error correcting codes. We add redundancy, we store more information to detect and correct the errors. The other type of errors are direct errors, that we access the device, but what happens is not what we expected. For memories, we wanted to write 0, and accidentally it was written 1, for example. In our case, for processing, we wanted to calculate. The output was supposed to be 1, but we got 0. So we did an operation, but we didn't get what we want. And usually the solution is also using redundancy, but redundancy in the operation itself. For example, triple modular redundancy means that we will perform the operation 3 times, and then we'll vote. We'll take the majority of the results, assuming that the same error won't happen twice. And if it will happen, then the probability for that is much lower. But when we talk about processing memory, those solutions are becoming less trivial. And I will explain why. For error correcting code, when we do it for memory operations, then the idea is that every time that we write to the memory, we also write the error correcting code bits. So that happens during the write operation. We just write more bits than the real data. And when every time that we read also the ECC bits, and then we perform the detection and correction if needed. But in processing in memory, we don't write and we don't read. We don't want to do external operations. We want everything to be inside the memory without knowing what are the values. And this complicates things. So we can think about doing it within the memory as part of the computation, but it's not that trivial if we want to support strong codes. Because if you think about row parallelism, for example, so you can say, OK, and within the row, we will have also ECC bits, so we will add some additional operations to calculate also the ECC bits and performing XOR operations, for example. But then usually the code won't be strong enough because everything within the same row. There is a strong dependency between the different bits. So what we propose to do is to work with diagonal codes. So basically, we mixed the different rows and the different columns within the code. And in order to do that, exploiting the parallelism of the mMPU, we separated the memory that holds all the data with the ECC bits. We call it check memory. And we connected them through shifters. So the connection is a connection that is programmable. And by that, we can connect them smartly to different columns. But since they are just connected together, then we can perform the computation that way. So throughout the computation, we can also perform within the memory the ECC calculations that are required, including the detections and correction. But everything is done within the memory by also rotating some of the bits so the code will be strong enough. And of course, this adds more latency, about 20% increase in the latency, but the reliability is substantially improved. I will show results in 2 slides.
So are you saying that there's some sort of dedicated hardware for doing the
Yes.
check memory? You could have maybe done it all explicitly with more operations, but since you know you always have to do it, we're going to bake it in for better efficiency?
Yes. For direct errors, we also use triple modular redundancy. And there are different ways to do that. One way is to do it within the same row. So we will have, you can think about that, having the 3 gates in the same row, paying 3 times the latency that is required. A different approach is to use row parallelism. So we will use 3 rows for 3 gates that will be performed. This way, the latency will remain almost constant besides the votes that are required in the end. But we will lose a lot of area because now we consume 3 rows instead of 1 row. Okay, that's the trade-off. And in order to evaluate that, we took a neural network just to have a benchmark. And we measured how much we improve, assuming that we have some probability for errors. And those are different probabilities for errors. And we measured across the time for indirect errors and for different number of operations for direct errors. And we see in brown, those are the results. And lower is better here. In brown, those are the results with the ECC. In blue, the results without with reliability mechanisms. And in blue, without. And you can see that we get a few orders of magnitude better results for the improved reliability. So that's about reliability. let's move to programming and architecture. And this is based on a paper that we had last micro that is called piping. The idea was to develop an end-to-end integration of the mMPU. And the idea is that the programmer will write in Python, just regularly on Python using tensor operations. And we developed a development library that can perform both the memory management, how the data will be mapped inside the memory, and also support the algorithms themselves. So the programmer will write that he wants to add 2 tensors, and it will be translated into the algorithms that are required specifically for the mMPU. There is a driver that takes the architecture, the instruction set architecture that we proposed, and translates it into micro operations specifically for the specific technology. In this paper, we did it for mMPU and NOR gates, but you can change the driver to support other gates or other mechanisms as well. And at the end, it can be either mapped to hardware, and we also built a simulator based on a GPU, so everything can be run to test the functionality and the speed, and you can also measure energy when you add models for energy. So let's start with the instruction set architecture and the microarchitecture. So for the microarchitecture, we basically support different micro operations from masking, so we can select and deselect different crossbars and different rows. So we don't necessarily need to do work on the entire memory, but you can, throughout those micro operations, decide how to mask some of them. We also support the conventional read and write operations of the memory. We support logic operations, either horizontal or vertical. For horizontal, it means that we also support partitions. So we can select the different partitions, and if it's vertical, then it's among columns, so you don't have partitions. And we also support move operations, so we can move between arrays. If we want to do it within the memory, within the same array, then it's logical operations. So think about, for example, performing 2 NOTs in order to move data within the array. But if we want to move between 2 arrays, then it requires a dedicated micro operation. So in total, we support both read and write operations, just like a regular memory, and also processing in memory operations, including partitions. So this is the microarchitecture. For the instruction set architecture, the idea was to use terminology that is similar to GPUs. So a crossbar is like a warp, and every row is like a thread. So from the programmer point of view, he has threads and warps, but it is mapped physically into different crossbars and different rows. And within the row, there are registers. So specific columns are mapped into registers, architecture registers. So this is how the programming is mapped into the physical structure. And in the instruction set architecture, we support the different arithmetic and logic operations, both for fixed point and for floating point. So from the programmer point of view, R-type instructions are mapped into registers with the threads, and the same goes for the move instructions. So we can move from one register to a different register in a different thread if required. So that's about the microarchitecture and the instruction set architecture. And for the development library and the driver, the idea is to write or to use this mMPU as a tensor accelerator, basically. That's the views from the programmer point of view. And the programmer can write the operations that he wants to do, and then it is translated to the R-type instructions. And also there is support for inter-crossbar communication. So if the mapping of the data requires moving from one array to the other, this is transparent from the programmer point of view, but it translates into to instructions or macro instructions in the architecture to support the move operations that are required. And you can see here an example of how the mapping of the different crossbars goes. So there are addresses for the crossbars. So the addresses of the memory are also mapped to the number of the crossbar. So it will be possible to move them efficiently if required. And the driver is the ingredient that its role is to move from the architecture to the microarchitecture. So it's tailored to the specifically, in this case, to the mMPU. So the idea is to take the instruction from the instruction set architecture and map it into the micro instruction of the microarchitecture. For example, we want to do a division, then it becomes a set of NOR operations, and we relied on arithmetic as the basic development for arithmetic operations. For logical operations, it's even much easier because it's either explicitly the same gate or a small set of operations for the gates. So that's basically piping. And of course, in the paper, we also show the simulator and evaluation and all those kind of things, but that's more straightforward, I think. Yeah.
So you have you have a compiler that, so if the programmer does nothing, it will try to intelligently map it,
Yes.
knowing what the architecture
Yeah.
is. And maybe you're gonna, so how much benefit, like you can imagine a programmer who sort of knows this architecture, knows everything, writes writes most of the code in these low-level instructions, or someone who, or your automatic compiler.
Yeah, so
Do you have a
you
sense of
can
how
think
much
about the
difference there is?
library as this programmer that did that, basically, right? The library, the development library is basically this smart programmer that did it more specifically, right? That's basically what, so you can extend the library.
How much improvement can you get from writing the code yourself versus using the?
So it really depends what you want to do. If you want arithmetic operations, so we believe that it's optimized for, at least for this specific technology. If you want something completely different, then you may, like matrix multiplication maybe, or something like that, then you can. Oriana, and I didn't show it here, Oriana had a paper also specifically about matrix multiplications, and is doing mapping of matrices in a much smarter way to support that. And actually, in 3 slides, I will talk about this work more from the output of that, not how we did that, but what were the results. Because specifically, matrix multiplication is probably not that attractive. Okay, so before I will conclude, I want to talk about 2 applications. And the first one is relational databases. This is actually the results of a PhD from a student named Ben Perach. And Ben explored databases. And you can see here, there's of course a lot of work behind it that I won't cover, but he got, relational databases seems like an attractive application because at the end, it is a structured database because everything is tabular, so it's exactly organized the way that we like in terms of exploiting parallelism. And we want to do the same operations across all the different elements. And this means that when we run a query, basically we can benefit a lot from the parallelism. And the data movement is minimal. And by the way, more than 99% of the improvements that he got was from the reduced data movement and not from the calculation itself, which is pretty simple, but also processor can do it very fast. But the fact that at the end you get, for example, a single result out of many options reduce the data movement substantially, and that's most of the benefits that we got. So you can see on the top results for TPCH and on the bottom results for SSB, different benchmarks. And you get, I don't know, between 5 to 10x performance improvement. Compared to large, sophisticated hardware, because those machines are usually require a lot of memory, a lot of processors. So at least in theory, the mMPU should be much cheaper and easier to implement than those machines.
So Shahar, for this type of benchmarking, what type of memristor are you using? So I'm basically thinking, the contribution could be from architecture side.
No, here it's all architecture.
So this is all using CMOS, using SRAM based?
No, it's using resistive RAM.
So that is a different technology.
Yeah, it's the mMPU model. The mMPU model that I showed. But this work is mostly on the architecture side.
But it's kind of, if you think about in terms of the total runtime, part of a runtime will also based on how.
Yes, so that's what I said, that actually 99% of the benefits here are not from, I mean, it doesn't matter if it took me 10 cycles or 100 cycles, because the big advantage is reduced data movement. Because if you think about it, in a von Neumann machine, what you need to do is to read from the memory, perform like in those benchmarks, usually you do some comparisons mostly, because you need to, TPCH, for example, is finding a stock in a store, basically. So you need to find something in specific date, that they bought more than 10 ingredients from the store, okay? So you need to do a lot of comparisons. So
And then how big of a crossbar are you assuming here? Is that
I think it was 512 by 512, something like that. Actually, one of the things that we did was to represent the data in a way that is more compressed, to be able to have everything inside a single row. For TPCH, for example, we were able to do that. Otherwise, you need to move some more data. But the main benefit, again, the operations, there are very basic arithmetic operations here and mostly logical operations, because again, it's mostly comparisons and small comparisons. So it's not about the logic itself, it's more about data movement.
Yeah, but then because you will have the database itself will be very big, right? It
Yeah,
cannot
so
be
that's why
all-
you need, that's the advantage, because you're using, anyway you need the memory, right?
So you're
Even if it's a von Neumann
all
machine.
the data are in the.
All the data is stored inside the mMPU. Yeah, otherwise you need to move all the data, and then that's the same movements that you would do in a von Neumann machine.
That, okay, that makes sense.
Yeah, everything is stored, like the entire database is stored in the memory stores. Yeah, otherwise, it's just the same movement.
Exactly.
Okay. That's on, actually, in the paper, we actually we stored in the memory stores only the things that are required for the query, because there is a lot of other data that, for example, you want the ID of someone, and if you find a match for this ID, maybe you need a lot of data that is not part of the computation, so this can be stored in a DRAM, for example. Okay, if you want to save, but it really depends on the benchmark. Okay, so that's about databases. Another thing that people, where everyone wants to accelerate is neural networks. And in 2019, there was a paper in ISCA that they took magic and they accelerated the training of deep neural networks. It's before LLMs. And they showed, you can see the results. They improved compared to GPU by about 100 times the speed. And in energy, it's also around 100 times better in the energy compared to a GPU. And when we saw this work, of course, on the one hand, we were excited because it took magic. They basically took our work and showed that it's much better for neural networks. But on the other hand, I was very surprised because, of course, we also tried that. And we didn't succeed to improve, definitely not like that. And the last work that Orion did in his PhD was to explore that deeply, to understand it fundamentally. And what he did was to explore the fundamentals of processing memory in that sense through convolutional neural network. So the first thing that he did was to check the arithmetic, which is basically arithpim. It's a different way to present the results of arithpim. You can see here addition, multiplication, floating point addition, floating point multiplication in terms of throughput and energy efficiency. And just like the results that I showed for arithpim, here we win big time compared to a GPU. Assuming that the GPU also just need to perform additions or multiplications. And even if we don't take memory stores, we take DRAM like what Onur showed, then DRAM is the way that you perform DRAM is slower, but it's still, at least in additions with integers, for example, it's still 10 times better than GPUs. But for neural networks, we need matrix multiplication. So if we take matrix multiplication for different sizes, okay, from 32 by 32 to 2000 by 2000, for 32 by 32, we still win. But as the matrix becomes larger, then the results becomes worse. Okay, this is a GPU in our experiment, and this is a theoretical results for GPU, assuming that the bandwidth is infinite. And you can see that with the mMPU, it is lower than GPU in experiments, and with DRAM, it's much worse for large matrices. And the reason is that because that GPUs have good bandwidth, so they can perform a lot of computation, and the data is ready for the matrix multiplication, while in the mMPU, when we perform matrix multiplication, we can't exploit the parallelism now, because we still need to move the data inside the array, because the data cannot be organized in a way that we can have parallelism all the time. So now we need to add a lot of data movement within the array, or between arrays if it's a large matrix. If it's a large matrix, then it cannot even be in one array. We need to move between different arrays. So we add more data movement into the processing in memory, as opposed to GPU that still needs to move data, but it moves the data and it has HBM, so it does it in a fast manner. And if we take the entire model, then it's even worse. Okay? So fundamentally, it seems like that neural networks are not a killer app for mMPU, or stateful logic. Yes?
So I imagine you used 2D matrix multiplication, so Cannon-like or Sumo-like algorithm. How would you model the communication cost, the data movement with algorithms that are that potentially can give better performance? So either 3D matrix multiplication or abstraction-like matrix multiplication.
So that's a good question. We haven't explored that, so I don't have an answer that I can immediately answer. Yeah.
Well, okay, so you kind of did this thorough study. What's the resolution to the earlier results that you cited that showed like factor 100 improvement?
So I want to add that also the results from ISCA were before Arithmetic. So actually they said that they cannot perform floating point addition with magic simultaneously, like what I showed with the variable shifters. So they, for floating point additions, what they did is actually to move it outside of the memory. So with Arithmetic, those results should be better than their results, okay? Because we improved the algorithm. I think that what they did in the paper was that the GPU benchmark was with a lot of data movements that was not required. That's my impression, okay?
I see.
That's what we concluded, okay? But they have like 500 citations. Which says that with magic you can improve neural networks by 100 times. So I can't complain. Okay, and it's still under review, this paper, so I hope that it will be published soon.
Question?
Yeah.
So here, the cost of the operations, so still there is no data movement, right, in your implementation?
So there isn't data movement internally because you need to organize the data for getting parallelism, right? Because we get the parallelism only if the data is organized in a nice way.
And that's the expense.
That's, yeah.
That's what's going on.
Yeah. Okay, so to conclude my talk, so we saw that emerging technologies together with a new architecture allows us to do processing inside the memory or real processing in the memory. I talked mostly on the algorithmic aspects and the architecture aspects, but what we are doing in my group is trying to deal it with the entire stack. We have a lot of experimental work, making it really work on the different technologies because, as Sharon asked, right, at the end, the technologies really matters, and when we talk about reliability, we also need to understand the reliability issues, and actually they are dominant. That's maybe the main limiter for making it, functional today. Mark talked about it, I think, a lot about how to make a new technology really feasible. That's a real obstacle. So we also work on that a lot, and also on everything in between, the controller design, the circuit aspects, up to the software and the architecture. So in order to do that, I need to thank all the students that are actually doing the hard work. Thank you.
Maybe it's not important, but so it's supposed to be non-volatile. So if you crash, you have the But you have this parallelism, and the error correcting code is in another part of the memory. So if you crash and it's not written consistently between the error correcting and the original thing, what will happen?
Yes, so that's not only about error correcting, it's in general, right?
Yes.
So we actually had last year in HPCA a paper about those kind of aspects, about consistency and coherency, and also if you want it to be part of a system, or multi-core systems, then some of the data may be in caches. There are many aspects that are related to that. And I can't say that we solved everything. That's
So it's
definitely,
in the work.
it's part of the work, yes.
But is the non-volatility really fundamental to what you're doing?
No.
I mean,
Yeah, I mean-
it might, in some applications it might be nice, but all the computation in memory you're doing, none of that really depends on
I
that.
think it matters from two aspects. One is energy, because again, you have a lot of memory you not necessarily use all the time, so the fact that it's non-volatile
You don't
gives
pay
you
the DRAM refresh.
exactly. That's one thing. And second thing is non-volatility comes here anyway, because almost all of those emerging new technologies are non-volatile by its definition.
So one of the nice things about your design was you weren't like adding a lot of logic. You just said, hey, by the way, notice it's sort of embedded in here, except for some of the partitioning stuff. So can you experiment with real off-the-shelf chip? Maybe you don't get all the capabilities, but you could do some of these operations with an off-the-shelf chip or not?
So the question is, what is off-the-shelf
Well, I
chip?
don't
So,
know.
so
That's-
Onu talked about DRAM, for example, and he showed that for DRAM you are able. I think that the main issue is still both for DRAM and of course for emerging technologies is reliability.
Right.
So you can write, if you remember, Onu showed the DRAM stuff and he said that you can do it on commodity DRAM with 99.8% reliability, which sounds high, but it's actually low. And with emergent technologies, it's even lower today.
So I also maybe you talked about dereferencing. What happens if I want to do garbage collection and I want to dereference pointers in order to mark?
So we haven't explored that yet.
So, I mean, I guess I imagine there's some operations that are not. Does it make sense to have like this and a regular, memory and move the data back?
So I think that one of the advantages here, you see the slides that I didn't show, that it's completely backward compatible, right? You can ignore this, and then it's just a regular memory. So besides the fact that you need to support, like with partitions, like additional control, it comes for free, basically.
I see. So you can sort of turn off these.
You can decide that it's a regular memory, and you won't notice.
And it won't be worse than
Yeah.
a regular. I see.
So just a comment. I think you have another big advantage, that you have predictable delay because you are in a matrix-oriented structure.
Yeah, that's true.
And that can help a lot to work closure.
Mm-hmm. Yeah, good point. Yeah, sure.
Yeah, I think you showed your two applications. One is really good, right, the database one, and then the other one
Yeah.
doesn't seem to be. You think there may be a general way to look at what type of application or what type of workload your will be better and
So
more quantitative comparison?
yeah, so Ronnie has a paper that's called Bitlet, which is an analytical paper that he developed a mathematical model to explore what is the sweet point between von Neumann machine and processing memory, and there are several characteristics that are required. For example, low computational complexity. Like if you are doing floating point operations, then you need a lot of steps in order to compute. But if you just perform XOR operations, for example, then you benefit much more. So that's the kind of characteristics that are required from an application.
Or could I use like what Dave Patterson was talking about, those roofline model to?
Yeah, roofline model. We show also there in a roofline model. And for example, another application that we explore is genomics. Because in genomics, if you think about that, since every character is only 2 bits, because there are only 4 possible characters, then all the operations are very, very simple. There are a bunch of a few XOR operations, basically. So, and there is a large amount of parallelism. And when you use von Neumann machine, since if you want, for example, to compare two DNA sequences, the amount of data is exploding because it checks all the options. So this is another attractive application. You can reduce data movement, and also the logical operations that are required are very simple.
Let's thank the
Okay,
speaker.
thanks.